I'm spending the rest of this lecture kind of reviewing the main concepts, okay, to get you all guys up to speed again. And I apologize لو الموضوع فيه repetition للناس بس at least you're refreshing some memory. So we're starting off. Remember, يعني, the general problem is an n-body problem. Okay, that you have a satellite, the Earth, the Sun, the Moon, planets, and whatever it is. Okay, and they're all active. Technically, realistically, we cannot turn off any of the bodies, so they're all active. If I were to write the force of gravity on body 1, okay, this is equal to the, well, to simplify it, let's say on body 1 from body J, for example, okay? So this is equal to G M1 or Mi Mj, okay, divided by Rij cubed times the vector Rij. Okay? Okay. I can rewrite this as negative Gm1 or Mi Mj, but Rij cubed Rji with the negative sign over here. Okay? Ijji, okay, this is whatever, so Rij is equal to Rj minus R. Okay? It's pointing from I to J. Okay? So whenever Ij means pointing from I to whatever J is. Make sense? Yeah? Alright, so if I were to write the total energy, say that total, this is equal to the summation, okay, so negative G Mi times the summation of Mj Rij cubed Rji, okay, or the summation for J is equal 1 to N, where J is not equal to I. Okay? Okay, so I can divide this by m to find the acceleration. So r double dot of I is equal to negative g. Okay, I'm dividing by mi. So j equals 1, j not equal to I to n, mj rij cubed rji. Okay, so as you see this equation right here, okay, this is the general form for the acceleration of any body, okay, I, okay, in an n-body field. Okay. How many degrees of freedom does this system have? It has 6 degrees of freedom, right? I have a second order, okay, differential equation. I have 3 degrees of freedom in position and 3 degrees of freedom in velocity, okay? So I have here 6 degrees of freedom, okay? So I remember the one session, I don't remember if we had 1 or 2 sessions last semester, and we had the discussion of, is the system solvable? Can I solve this equation? And when I say solvable, I mean, is it solvable in an analytical algebraic form? Okay, we can solve anything numerically. This is not the issue. Okay, but when, like in celestial mechanics, when we say, is this system solvable? We're asking, is it solvable in a closed form or an analytic form? Okay, usually there is no universal definition of what a closed form solution is. Okay. But there's an agreement on what it is not. Okay, it's not summation. It's not an integral of some sort. It's not limit. Okay, it needs to be algebraic relationship defining R, okay, of I at some point in this space. Okay, all right. So one of the ways. It's one of the ways to see or decide whether a system is solvable or not, okay, is the whole idea of integrals of motion. Okay? What does an integral of motion mean? So the proposition here is that if we have an equal number of integrals of motion equal to the number of degrees of freedom, then the system is solvable. Okay? But the question, once again, what is an integral of motion? An integral of motion is basically a constant of integration, if you may, okay, or a constant, okay, that relates one or two variables of my system over here. So if I would break this into its components, okay, we said that there are 6 degrees of freedom, right? So I have Rx, Ry, Rz, those are 3 degrees of freedom, okay? And then I have Vx, Vy, and Vz. Those are other 3 degrees of freedom. Okay? So if I can find an algebraic expression that relates any of these 2 or any of these 6 degrees of freedom together, any 2 of these 6 degrees of freedom together, okay, I basically reduce the dimensionality by 1 because I'm constraining 2 of them together. It's exactly the way you're solving simultaneous equations, okay? That if I can relate, so I have 6 variables over here. Every time I can find an expression relating this one to that one, for example, I just reduce the dimensionality by 1. صح كده? It's no longer 6 degrees of freedom because one of them is constrained. And if I find another one, I reduce the dimensionality by 1. And so on. Okay? So if I can have 6 constants, okay, that relate, or 6 expressions, okay, independent expressions that could relate these variables to one another, then I can.
constant في السيستم كله.
Yes.
whatever الستيت بتاعت السيستم دلوقتي ايه.
That's true.
تمام. حضرتك دلوقتي.
هي زي يعني when you integrate, when you say plus c plus a constant, it's kind of like the same. It's the constant of integration.
انا مش عارف بقى يعني الحته دي بتكونفيوزني شويه بقى الحته اللي هي constant of integration يعني constant يعني constant of integration.
Hey, it's not, أنا بقول it's similar. It's not a constant of integration, but we call it an integral of motion because it's a constant. Yes, it's relating variables. Okay, Rx and Vy, for example. If I can relate Rx to Vy, I just constrained. Okay, so I have an expression. Okay, and it's equal to a given constant. Okay, so if I can derive that a relation between Rx and Vy, and that expression algebraic, and there's a constant there, okay, we call this constant an integral of motion. This expression right here, okay, so if I can write this as, okay, function of Rx and Vy, okay, is equal to 0. Or equal to constant, whatever a constant is. Okay? Then I basically constrained Rx to Vy. Okay? So the dimensionality of my system was reduced by 1. Okay? Every equation that you get, you reduce the dimensionality by 1. So every equation, every expression represents an equation, and the variables in the expression represents a unknown. Okay? So if I want to solve for those unknowns, if I can find, if I have 6 unknowns, then if I can find 6 equations, independent equations, okay, relating those 6 unknowns together, then I can solve the system, يعني equal number of equations and equal number of unknowns.
The six algebraic equations and the 6 unknowns, this fully constrains the system. Okay, I'm standing in one point in the state space. Unless we're talking about specific instances in time. Okay. Yeah, if I'm saying that Rx.
The constants, okay. So if I say okay, so let me say. I'm not sure if this is answering your question, but if like one of the constants, for example, is energy. Okay, which is true, and that if this is a closed system, the mechanical energy is conserved. So, regardless of where your location is, your R and V change in the system. Okay, but that relationship holds. Okay, so I always have a relationship between, regardless of where you are on this map, okay, there is a relationship that constrains what kind of velocity you could have. You cannot just randomly, once there's a defined motion, okay, and there's a constant for that motion, one of them is energy. Once your location, which means your potential energy, is given, okay, that constant motion constrains the magnitude of velocity that you can have in this system.
Is the relative magnitude between the velocity and the position
Yeah.
vector? My question is it necessary for يعني هو انا شايف ان هو عشان انا define the system 6 algebraic equations يبقى انا كده fully constrained الموشن في point واحده بس لان هو الالجبريك system دوت will only have one solution if it's solvable يعني.
I see your point, بس ما عنديش straight answer at this point. Do you guys see the point? Does it make sense? Am I missing something?
هي 6 يعني 6 linear equation في التايم التايم لما تتغير انت يعني
So one point at a time كل مرة.
So لسه يعني
Maybe this is what I'm trying to say. And that your Rx and so for any given set, okay, once one of these variables is known, okay, with my constants of motion, then the rest should be constrained to these sets.
specific point in time.
بالظبط. Right. So time changes. Every point in time defines a different set of parameters. Does that answer your question, Holmes?
Yeah.
Okay. So for every given point of time, yes, the motion is constrained because of the. And this is how we define motion. This is how I can predict. I cannot predict to say, either this or this or that. To be able to predict, I'd be able to solve it. That in the future, it's going to be at this location at this velocity, so it must be constrained. Make sense? Okay. So the whole thing about integrals of motion is not a necessary condition, but it's sufficient conditions for solvability. Okay. It's one of the ways people solve or find analytical solution. So up till this point, up to this moment, okay, we haven't been able to find a solution for the n-body problem. And the reason is, okay, so I have a 6 degrees of freedom for R1 or Ri, okay? But Ri is also a function of the location of Rj, which is j going from 1 to n except for I. Okay? So I cannot just solve this equation independently because this is not constant. Okay? So I need to find the equation for Rj, where j goes from 1 to n and j not equal to I. So I need to write an equation for R1, R2 double dot, R3 double dot, R4 double dot, up to Rn double dot. Each of these equations has 6 degrees of freedom. So my system as a whole has 6n degrees of freedom. Okay, so this is the equation of motion for one body, mi. Okay, mi is a function of the locations of mj, whatever j is a function of location of this and this and this and all the other m's in the system, right? So I need to write an r double dot equation for each of the bodies in the system from 1 to n. Okay, so I have n second order differential equations. Okay, each of them has 6 degrees of freedom, so a total of 6n degrees of freedom. Yeah, right. So I'm not going into the derivation much at this point. But what we've been able to solve, okay, are a conservation. So the constants that we're able to solve for is conservation of linear momentum, okay, and from which we're able to basically that the summation of m r double dot, okay, is equal to 0 because I'm summing all the forces in the system, okay, and for every Fi1 there's an F1i that cancel each other, okay, so the sum of all the forces is equal to 0, okay, and if I can integrate that over here, okay, I can get that, okay, so this is m r I dot, okay, plus some constant over here.
Doctor, about conservation of linear momentum and angular momentum.
This one is linear momentum. In the n-body problem, there's a linear momentum is also conserved. Okay, so I'm not going to go. Actually going to ask you just as a first exercise, Yani, today is to derive the constants. You can find them in references, but suggest so you can understand it while you derive it yourself. Okay, but basically, if you go through this and then I can integrate again, and I get mRi plus when you're integrating c times t plus another, so call that c1, c2. All right. It ends up that each of these constants, okay, are the position and velocity of the center of mass at the initial time, whatever t naught is.
What are we supposed to find in the references?
This, what are we supposed to find in what?
In the references, you said something.
Oh, the derivations, the derivations for those. The detailed derivations, I don't want to go into that because I want to jump into something else. But basically, going through this derivation linear conservation of angular momentum, conservation of linear momentum, it shows that the center of mass, okay, the acceleration of center of mass is 0, okay, of Ri double dot is a function of Ri j over here, okay. Okay. Again, the whole reason because you have an so Ri cross well.
I dot with R dot.
So say that again.
So R, it's summation of M R dot with R double dot.
No. R double dot crossed with R, but again, I don't want to go into the details of the thing, but basically you have over here the Ri, okay, you have Ri minus Rj, okay, and when you sum over all the J's and all the I's, okay, this goes to 0, okay, which means that, yes,
Let's know if I get what does this do?
what is that one?
What does this do?
Man, I'm getting there. I'm just saying that if I take the total force acting on body 1, okay, and cross that with Ri, okay, if I expand this and do the summation over all the J's over here, okay, this expression goes to 0, okay, and then I'm looking at this expression right here, okay, and this is equal to d by dt, okay, m of r crossed with r dot, okay, because just to show that this is r dot crossed with r dot plus r crossed with r double dot. Okay. R crossed with r dot, if I take the differentiation of that, is equal to r dot crossed with r dot plus r crossed with r double dot. Okay? So what we're saying here is that the derivative of r crossed with r dot is equal to 0. Okay? Which means that angular momentum for the system is conserved. Okay? So angular momentum is a three-dimensional vector. You have 3, 3, and 3. That's a total of 9. Okay? And the final comes from the energy, conservation of energy. I'm not going to derive that here. But again, because we derived those last semester, I don't want to do them here again. Yes?
First of all, did we assume for linear momentum to be conserved, or did we prove for it to be conserved? The linear momentum.
No, we didn't assume. We just took the so the summation, okay, of all the forces, okay, over Ri is equal to 0 of the system, of the total system.
How do you know that?
Yeah.
Because huh?
External forces.
You have a force from this direction equal and opposite in this direction. Force and equal and opposite, force and equal. So if you sum all the forces across all bodies, then the total equals to 0.
The second question, how did we reach the first equation in random?
This equation? No, I'm just saying, I'm taking this and cross multiplying with Ri. It's just a manipulation.
And it's also equal to 0?
Yes, if you do the summation and across all j and i's and so on, because of this relationship, the ij and ji are opposite to one another, so they cancel each other out. I want you, I just don't want to do it here. I want you to, I have it. I just want you to practice it so you can follow the process and grasp the concepts at home. I just want to work with the outcome of that. Someone had a question. قولي تاني؟ References. يعني by the end of every lecture, as we agreed, بيكون يعني the chapters and the books that we've covered. تمام؟ طيب.
معلش
قول.
why is linear momentum the second differential of distance and time? Why is it not m times r dot t? يعني linear momentum m of v مش m of a.
This is ماشي. انا كل اللي عملته ان انا integrated this عشان اوصل لده. هنا this is equal to 0. يعني انا ببتدي بده وبقول ده equal to 0. So I'm integrating this. I got the linear momentum of the system. Okay. يعني is equal. You have plus c is equal to 0. يعني or plus another constant. So linear momentum is a constant.
So conserved is not necessarily 0.
No. It's just a constant. It depends on the initial state of your center of mass. If your center of mass is initially stationary, then أنا قلت إن هنا أنا عندي هنا these are vector integrals. Okay, I have a 3 by 1, a 3 by 1, okay, and a 3 by 1 in the angular momentum. Because the angular momentum is r cross 3, so this is a 3-dimensional vector. So I have 3, 3, and 3. That's 9. Okay, and then I have conservation of energy. Okay, that's 10. Okay, are you guys good? Okay, so I have a total of 10. Gals, please. So I have a total of 10 integrals of motion. To solve the n-body problem, I need 6n integrals of motion. Okay. Up to this day, no one was able to find more integrals of motion for this system. It doesn't mean that it doesn't exist, but very smart mathematicians have tried and failed. But you can try if you want. It's up to you. عشان أنا عارف إن أنتوا بتسمعوا كده. طب بقى أنا بالذات الواد ده.
بصوا يعني مثلا لو عملنا ريدكشن مثلا ل 2 بودي موشن مثلا او 3 بودي موشن، هل ممكن احنا نقدر نبريدكت الايرور اللي هيحصل مع الاكشوال بقى لو هو مثلا بنتكلم في بودي مثلا؟
You mean analytically? Derive an analytical expression for the error? An analytical expression? I'm sure there is. I've never used it. But we do a lot of numerical things. But I'm sure there are some analytical expressions for it. Okay. All right. So up to this point, we're unable to find a closed form solution for the n-body problem. We just don't have enough integrals of motion. Okay. The lowest number for the n-body problem is 2, which means that you need 12 integrals of motion. Right? We only have 10. So even the general two-body problem is not solvable analytically. Okay? Which we start looking at the relative restricted two-body problem. Okay? So the relative motion, okay, that I have R12. Okay, so let's assume I just have, well, I have more than one body. Okay, I'll keep the n-body problem. Okay, but let's assume that one is the Earth, two is your satellite, and then everything else is like the moon and the sun and planets and so on. Okay, so R12 is equal to R2 minus R1. Okay? This is equal to negative G summation of J equals 1, J not equal to I to the n mj rj2 divided by rj2 cubed. Okay? So this is basically the expression for R2. Okay? Right? Plus G, J equals 2 to n, mj, rj1 divided by rj. Okay? And this is the expression for this right here. Okay? The minus just cancels the other minus in the equation over here. Okay? I can just group things together, okay, and simplify this into, I'm going to skip a step, but basically I can simplify this into, this is equal to negative G, M1 plus M2, okay, divided by R12 cubed times R12, okay, minus J equals 3 to N G M effect. Yes.
Why in the second summation is such a
Say that again.
in second summation, why is J from 2 to n not from 1 to n?
علشان 1 يعني it's R1 double dot. I can say from 1 to n, but J is not equal to 1. عشان it's already for body 1.
So for body 2 we're going to
So ما ينفعش يبقى عندي R11. Does that make sense?
okay, for body 2 then we're going to skip number 2.
So for body, yes, this
J
is
not equal to
J
1.
not equal to 2. Yes. تمام? So far so good? Right.
How do you extract the...
Over here in this summation, I have when j equals to 1, I have a j12 over, R12 over here, and in this summation, when j equals to 2, I have a j21 over here. So I'm extracting those expressions from those summations, putting them outside of the summation thing, because I'm interested in the relative motion of body 2 with respect to body 1. Okay? So I extract those out of the summation, and then I leave the summation as the perturbing force, the indirect acceleration. So for a spacecraft orbiting Earth, there is direct gravitational influence coming from Earth. So this is, Earth is 1, and the spacecraft is 2. And then there is indirect acceleration coming from the sun, the moon, and then indirect acceleration affecting the Earth. The sun affecting the Earth, Mars affecting the Earth, and so on. Okay? So that's what we call indirect acceleration. This is my direct acceleration. تمام? Okay? In the case that I don't have any third bodies, then the indirect acceleration disappears, and I'm left with this right here. Okay? In the two-body problem, I'm just left with this expression right here. Okay? All right.
If I am neglecting the third body,
If
if I'm neglecting the third
yes.
body, indirect acceleration will
disappear. Okay. All right. Let me pull that. Okay. So let's look at. So we did. This is the general relative two-body problem, or the relative n-body problem. Okay. We're going to do the relative two-body problem now. Okay. So I'm neglecting those bodies, and I have r double dot is equal to negative g m1 plus m2. Okay. Divided by r12 cubed times r2. Okay. And for simplicity, because there's just 1 and 2, I'm just going to drop the subscripts over here, okay, and call that big M for the planet and little m for my spacecraft. تمام؟ Okay. So all right. We've shown that the center of mass in an n-body problem, okay, is moving at a constant velocity. It's conserved, the linear momentum is conserved of the system, which means that the center of mass is moving at a constant velocity. Constant velocity could be 0, but it's still a constant velocity. Okay? So, when I'm looking for, if I'm solving a Newtonian mechanics problem, okay, F equals ma kind of thing, okay, if I'm using Newton's law, okay, I need to derive those in an inertial reference frame. If the reference frame starts to accelerate or rotate or whatever, the equations of motion are no longer valid. Okay? So it's a safe choice to pick the center of your reference frame to be at the very center of the two objects, okay, or the center of mass of the two objects. If I put the origin of my frame there, regardless of what's going on in the motion, it doesn't matter because my barycenter is not accelerating. Huh? It is inertial and it's not accelerating, so that works. تمام؟ huh?
لو صن وإرث هنعتبرها الصن.
Barycenter. Regardless, barycenter is still inside the sun, but it's not exactly at the center. But same as for the Earth and Moon, the barycenter or the center of mass between the Earth and Moon is like 2,000 kilometers beneath the surface. So it's 4,000 kilometers from the center.
المفروض السولار سيستم أصلا مش بيلف حوالين الصن نفسها صح؟ البوينت براها شوية.
Again, it revolves around the barycenter, yes. So the barycenter is not necessarily at the center of the sun. It's not at the center of the sun. And the moon is not rotating about the center of the earth. So if you want to look, if you plot the motion of the earth and the moon, okay, we think, I mean, you're looking at the moon, so you have a reference frame on the earth, you're looking at the moon, you see the moon going around you in a circle. But if you're looking from an outsider view, so you fix an inertial frame outside the earth and the moon, you'll see that this is, I'm just going to use a point mass just to make my point clear. Okay? So in reality, if this is the earth, this is the very center of the earth and the moon. Okay? It's slightly, it's not slightly, it is off center. It's about 4,000 kilometers off center. Okay? So if I just condense the earth into a point mass, or here, and here is the moon point mass, okay? Assuming that the very center, okay, that's somewhere here, the earth is rotating a circle and the moon is rotating in a circle about the very center. Okay? So in reality, this is what's happening. But when you're standing here, you don't see that. Okay? You only see the relative motion. So you don't see the inertial motion over here. Okay. So let me just. Okay. So we talked about the integrals of motion. In this case, how many degrees of freedom does the system have? Have 6 degrees of freedom, and it's only just one equation, so 6 degrees of freedom. So I basically need 6 integrals of motion, right? It turns out that energy is conserved, okay, but I'm not gonna dig into that because we already know that, okay? And
we have two bodies.
we have 2 bodies.
So we have 12 degrees of freedom. But the n, this is n minus 1.
We conserve the.
So you're looking at you're looking at the relative motion, okay? So you're just looking at the motion of one body with respect to another. So you're not interested in the motion of the central body. You're interested in the motion of the other one, the relative motion. That's the whole thing. And I cannot solve the general two-body problem. I can solve the relative two-body problem because I can ignore the second body. Okay? So right now I only have 6 degrees of freedom for M2. I don't have degrees of freedom for M1.
Does this have to do with picking our coordinate system in the barycenter? يعني أنا كده I take my coordinate system body.
Oh, actually, so the assumption that we make that M1 is much, much smaller than, I'm sorry, M2 is much smaller than M1, that it doesn't affect the motion of M1. Okay?
So we're assuming that the barycenter is at the center of the bigger object.
You can think of it like this right now, but yeah, we're going to talk about this later as well. But even if you don't have to make that assumption, okay, we are looking at the motion of one object and not the other. Okay, I'm not interested. My R is measured from the center of M1. Okay, so regardless whether M1 moves or not, my R is still the same. Okay? I don't need to worry about the degrees of freedom of M1. If I choose that my location for the axes, okay, is at the center of M1, then I don't have to worry about the motion. Another way to think about this, let me try to visualize. If we hypothetically can find a truly inertial reference frame, which is not necessarily a real thing, okay? But let's assume that we're able to define that, okay? In which frame I have M1, or call it big M, okay? And I have little m over here, okay? So I have R1, and I have R2, and then I have R, okay? Let us assume, okay, that you can place another reference frame, okay, parallel to this one, okay, and it's not rotating. It's not going to rotate. You're always going to fix. So, and this is what you can choose. I'm going to define the motion in a non-rotating frame fixed out of the Earth, whether the Earth moves or not. And this is why we use, if you guys remember, we use the vernal equinox, and because it's fixed and so on. Obviously, so this is not changing, and this is parallel to it. It's not rotating. The coordinates of R here is identical in the blue frame and in the big red frame. Okay, so if I can drive my equation, so I know that if I drive it here, it is definitely inertial. But if I can attach a parallel frame, non-rotating parallel frame to the Earth, I can still assume that the R is the same whether it's defined in this frame or defined in the other frame. Does that make sense?
Non-rotating or non-accelerating or non-rotating?
ما هو non-accelerating, yes.
كده السيستم بتاعنا ده مش هينفع غير لبادي تو باديز واحد الفرق الناس كبير جدا بينهم ولا ايه؟ بحيث ان احنا حطينا البريفوكال
لا هو again يعني once you think about it this way you don't have to worry about this assumption.
احنا مش قلنا ان احنا لازم نحط الكوردينيت سيستم في البيري سنتر بتاع
أنا بقول إن yes the barycenter is a very safe place to place it علشان you know that by definition the barycenter is an inertial point يعني إن هي it doesn't accelerate. That's what I'm saying here, okay? Assume that this is the barycenter. Just assume that this is the barycenter, okay? But you define the frame in this barycenter, okay? And then you just translate it, okay, to body M. Okay?
Translate it to where?
Huh?
Translate it to where?
To M, to the big body. Okay? Or draw another one, or attach another one parallel to the one on the barycenter, okay? And it's not rotating, okay? And fix it at M, okay? Regardless of the motion of M, okay? I'm looking at the relative motion of little m, of the satellite with respect to the large M, okay? I'm looking at that vector. Let's say M does move, okay? But when M moves, this vector in this frame is the same as this vector in that frame, regardless of the motion of M.
translation يعني للاكسيس اللي
Yeah, but so my point is regardless whether M moves or not, تمام? This vector R, let me just change the color. If my two frames, if this frame is not rotating, okay, and it's parallel to this one, regardless of the motion of M, M is going to move. That means that R1 is moving, that R1 double dot is moving, and so on. That's fine. Okay? But regardless of what happens, this vector, this green vector, is going to be identical in the blue frame and in the red frame. Okay? And this is all I care about. That means that when I measure R, okay, or R double dot or whatever, it is the same as if I'm measuring from a truly inertial frame.
This is an inertial frame.
Hmm?
Like an inertial, yeah, this is a frame where Newton's laws apply.
Yes. Again, I'm looking at the relative motion. Okay? I'm looking at the relative motion of M from the large of the satellite from the large body mass. I know that big M moves. I know that. Okay? And even when big M moves, the change in R when it moves in this frame is the same as the change in R it moves in that frame. Okay? So I can say that my R that I'm measuring here is equivalent to the inertial R of the actual inertial frame. Does that make sense?
Relative motion here.
بالظبط. Because it's relative motion, then it's the same. If it's not relative motion, then we're falling into trouble. Make sense? أي دخان. ورانا إيه؟ عقدها لكم إزاي؟ مصلحة. So I'm putting the extra frame so we can look at the truly relative motion instead of looking at the center of mass and saying, okay, this is the motion about the center of mass and this is the other motion about the center of mass. I just want to look at it. I can derive it in the center of mass, but then I can plot it in the. This is doing exactly the same thing. Okay? This is exactly doing the same thing. And how instead of plotting the motion about the center of mass, okay, by translating the reference frame to the, I'm just plotting it over around M1 or the big M. So I'm still visualizing the same inertial thing, but it's plotted with respect to a different origin. But it's still inertial.
The big frame is moving but not rotating.
Yeah, it could. I mean, M1 is moving. Yeah. Yep.
And the frame, the blue frame is moving with.
Yes, the blue frame is moving, but it's not rotating. Yes. And again, I don't care that it moves because it moves. حتى لو أنا باصص على هنا. Okay. Forget the blue frame. Okay. M moves. ماشي. M moves. Well, it means that R1 is not fixed, which is, we know that R1 is not fixed and R2 is not fixed, and I know that I have R2 minus R1, so I know that R2 double dot minus R1 double dot, this is what R is. This is my R right here. So I know that these guys move, okay? But what I'm saying is, if I attach a parallel frame here that does not rotate, then this green vector is identical whether it's represented in this frame or that frame. It just has a different origin, okay? But it has the same representation. Does that make sense? لو أنا مسكت ده ادي الفريم بتاعه اهو، okay? If I translate it هيبقى هو parallel دي بالظبط. وادي الفريم بتاعه هو يعني if I find the x, y, z components of this, it's going to be exactly the same. The same is true for R dot. The same is true for R double dot.
The idea behind it is not just to catch the
Yes, so I can just look at the relative motion and not with respect to the center of mass. Make sense? Okay, move on. All right. So in this case, in the case of the two-body problem, okay, relative two-body problem to be specific, we said we have 6 degrees of freedom. Okay, we do have conservation of energy. Okay. And we do have conservation of angular momentum, okay, which is similar to the quick derivation that we did over here, crossing the equation of motion with R and simplifying and things like that, okay. But then, just want to do a quick derivation هنا بسرعة, okay. If I get, okay, so I have an R double dot over here, okay. I will cross multiply that with R. Cross multiplying it with R. Okay, so this is equal to, I'm going to call this, okay, if M1, if little m is much smaller than big M, so this goes to 0. Okay, just for simplification, you can keep it or you can add them, but it doesn't matter. So Gm, we call this the gravitational parameter. Okay, so I can write this as R crossed with negative mu over R cubed times R. تمام؟ I'm just crossing this with r on both sides of the equation. Okay? So this is the same as d by dt r crossed with r dot. Alright? Let's say has. So this is the same as r crossed r dot time derivative of that, because this is r dot crossed r dot, which is 0, plus r crossed with r double dot, which is this right here. Okay? This right here, r crossed some scalar with r, this is equal to 0. So, okay? So I can basically say that this expression is equal to 0, okay? Which basically says that the angular momentum is constant. So far so good? Okay? I mean, I'm going to take that and take the r double dot equation one more time and cross multiply that with the angular momentum vector. Okay? Again, this is equal to negative mu over r cubed r crossed with angular momentum, which is r crossed with v. Yep. Okay. There's an identity here, okay, that I'm going to use. First of all, let me rewrite this as d by dt, okay, r dot crossed with h, because again, this is r double dot crossed with h, which is this right here, plus r dot crossed with h dot, and since h is constant, h dot is 0. Okay? So this is equivalent to that. Okay? And this is equal to, so I'm going to write an identity to this expression right here, so this is equal to mu over r cubed, and here's my identity, r dotted with, identity that I'm using here, it's not, can't explain it at this point. Okay? Type.
دكتور
Yes.
هو التحويله اللي هي من كروس لدوت دي بتيجي ازاي؟
This is an identity في linear يعني يعني مش زي ال trigonometric identities and things like that. So yes. هنا؟ هنا؟ لا ما انا بقول لك هنا ما كانش فيه d by dt. انا حطيت d by dt هنا. If I work this out, this is going to be r double dot crossed with h, which is this one right here, plus r dot crossed with h dot, which is 0. تمام؟
Parentheses ديت cross ولا dot؟
Dotted. These are dots. I'm switching from a cross product to a dot product. Okay. I'm going to get rid of this. So I'm going to take that. I'm going to work with this expression right here. Okay. And this is equal to negative mu over r cubed. Okay. And I'm just going to work this out. This is all right. So this is vector r dotted with vector r dot. تمام? All right. If I would, let me just draw this. Let me. مش لازم في البتاع. It's just a side note. If I have r dotted with r, this is equal to r squared. Okay? If I take the derivative of r dotted with r, okay, I can take the derivative of the right-hand side, okay, which is equal to 2r dot. Okay? But I also know that this is equal to r dotted with r dot plus r dot dotted with r. Okay, which is equal to 2r dotted with r dot. Okay? So I basically have that this right here is equivalent to this right here. Or in other words, r dotted with its derivative, okay, is equal to scalar r multiplied by the rate of change of scalar r. Okay? And there's a difference between, this is not the magnitude of that. Okay, and we had this discussion last semester. Okay, are you guys familiar with this? Yeah, have you seen this before? Ashan, we spent some time clarifying this. Is this clear to you? This expression. Huh?
This means in the name same direction. All dots are in the same direction.
أنا عشان حكايتي عشان الضغط يعني الضغط disappears.
عشان الماجنتيود بتاع left hand side
What I want to say is this is not equal to this. Okay? This is not equal to that. What this is saying, okay, this is the whole velocity, radius vector or position vector. Okay? This is the whole velocity vector. Okay? This is the magnitude of the radius vector. This is the rate of change of the magnitude of the radius vector. This is not the magnitude of the velocity vector. Okay? Because if I have, let's say, I have something moving in orbit. Okay? This is my r. Okay? Usually, my v is tangent. Okay? In a ballistic trajectory, my v is tangent. Okay? So this is my r. This is my r dot. Okay? My scalar r dot is the rate of change of the magnitude of r, which is basically the velocity component along the r vector. Okay? So for a circular orbit, r dot is 0. There is no component in this direction. But if I'm going on an elliptical orbit, okay, so it's something like that. So my velocity is over here. I have a component in the r direction as well. Okay? And there's a difference between that. This is the component of the velocity in the direction of r. This is not the magnitude of the velocity direction, of the velocity vector. Okay? But this is just a clarification that's important to make. Okay? So using that expression, okay, or that relationship, okay, I can rewrite this right here as r multiplied with r dot, the scalars, minus r squared times r dot. Again, this is r squared right here multiplied by r dot right here. Okay. Again, I can simplify this as negative mu. I'm just canceling some of the r's over here, so I have r dot times r minus r dot divided by r squared. Okay. You can work this out. This is basically the same as positive mu e by dt r divided by magnitude of r. If you derive this, okay, if you do the differentiation for this expression, this is the same as this expression over here. Tamam? Okay, so once again, I have the time derivative of, this is the right-hand side of the equation. Remember, this is what we're working with. This is the right-hand side, okay, is equal to mu times the rate of change of this. And the left-hand side is equal to the rate of change of that. So I can move all things to one side, and I have d by dt, okay, r dot crossed with h minus mu r divided by r is equal to 0. And I just moved. So this is the expression. This is the expression that I got over here. I just moved to the other side and took the derivative outside. So I have this expression equal to 0, which means that this expression right here is equal to a constant, because I can integrate it and say that equal to a constant.
Is there a physical interpretation of the derivative of r dot cross with h?
No. There isn't. It's just a manipulation.
It's purely mathematical manipulation.
Yes, yes. Okay, so this right here is equal to a constant. We call this constant the Laplace vector. This Laplace was the one who came up with it. Okay, can you tell me what units this constant have? What units does this have?
Has the units of has the unit يعني C has the unit of mu the gravitational constant.
Exactly, it has the same exact units of mu because this is unitless. The r divided by r is unitless, so I'm left with mu. Okay, so C has the same units of mu, which is actually kilometers cubed by second squared. Okay? All right. So if I divide C by mu, I get a unitless vector. Okay? And this is a 3×1 vector, by the way. This is not just a scale. Okay? Right? Yes.
That's one of the integrals as well.
Yeah, this is the B vector. Remember the B vector? تمام? Go ahead. Listen.
What did I get يعني from all of this information?
This is, okay, so I got, for the two-body problem, I got a new constant of motion right here. I had started with the h vector, okay, and that gave me 3 constants of motion, okay, and I was able to derive another vector, a 3-dimensional vector that gave me another 3 constants of motion, okay, and from this expression, we're going to derive the analytical solution for the relative two-body problem. Okay, so energy gives us constants, we'll talk about that in a minute. So Lisa gives you 6, and then the energy gives you 7. So you have, doesn't make sense, then the solution is not unique in that sense. You have 7 constants of motion and 6 unknowns. You have, so I have 3 from H and 3 from C. And we haven't talked about energy yet, so that means I have to. خلاص give me يعني بس 5 minutes كده يعني أخلص حاجة و then we can take it. All right, so I'm starting off just okay. So I have r dot crossed with h minus mu. R divided by r is equal to a constant. Okay, and we call that again Laplace vector. Okay, I'm gonna take the dot product of this with h. So I have r dot crossed with h dotted with h. These are vectors, right? Minus r over r dotted with h is equal to the constant vector dotted with h. Okay? What is this equal to? Oops. Yes. What is this equal to? It turns out, okay, I'm not, okay. H is equal to R crossed V, right? Which means that H is perpendicular to both R and V. Okay? Then I'm crossing V with H again. What is the, where does this vector lie?
The plane
This lies in the plane of motion.
And the plane of R and V.
The plane of R and V, yes, the plane of motion, right? And then I'm dotting that with H.
still the plane.
Huh? It is equal to 0. صح؟ تمام كده? Does that make sense? Okay. So this is equal to 0. Okay. What about this one?
دكتور معلش سؤال بس هو يعني هو البرايورتي في الكروس والدوت برودكت goes first to the cross product.
Here?
That's what we did here, so.
Here, يعني هو basically يعني ان انا I have initially اصلا ان I have كده و I'm dotting this with that. So priority yes goes to the يعني initially I have this.
Initially كان في parentheses.
بالظبط. يعني initially I'm starting with this right here and then بقول انا هاخد the left hand side او this expression and then take it out product of H. Okay? So this is equal to 0. What about this one? I'm dotting R with H. Again, this is also equal to 0 because this is in plane and this is perpendicular to the plane. Dot product is equal to 0. Okay, which means that C dotted with H is equal to 0, which means that it's constrained. C is constrained to H, which means that so we lose one degree of freedom, okay, which is replaced by the conservation of energy. So we end up with 6 intervals of motion and not 7. Make sense? تمام? What I'm saying is, this expression here, C dot with H, would prove that this is equal to 0 because those 2 expressions are 0. Which means that C is perpendicular to H. Okay? So they're not independent. So I have C is a 3 by 1 vector and H is a 3-dimensional vector. Okay? So initially we said we have 6 integrals of motion, but apparently there's a constraint on them. They're not completely independent integrals of motion. Okay? So that constraint reduces the dimensionality by 1. Okay? So we have, out of C and H combined, we have 5 integrals of motion. And then we have conservation of energy that gives us the 6th integral. تمام? Okay? Yeah?
Why is the second expression
Yes? علشان R dotted with R is in the plane, H is perpendicular, so the angle between them is 90 degrees, dot product is equal to 0. The angle between them is 90, and cosine 90 is equal to 0. Okay? Let's give me 1 minute now.
يعني عايز اعرف بس حاجه يعني مثلا حاجه زي كده يعني هي يعني مثلا هم يعني وصلوا لها عشان هم عارفين ان هو لازم يكون في ديبندنس لا حاجه رباني يعني.
Okay, so initially C is not, so when it first came out, يعني from what I've read برضو يعني عشان ما كنتش موجود. بس from what I read it was they're just trying to find constants. They're doing a lot of manipulations. This is why this necessarily makes sense. They tried several manipulations. They're trying to find an expression that they could integrate to find a constant, and وصلوا لده. Further manipulation saying, okay, فانت عندك دلوقتي طب ازاي ده انا عندي 7 وعندي 6 وبتاع, so we're looking for relations. I mean, this is the product of years يعني. It's not a. أنا ممكن أحطها لك midterm problem عادي, لكن هم يعني
دكتور معلش انا ما فهمتش ان هم perpendicular ان ده ان هم مش totally independent.
إن هم perpendicular, it means that they're not totally independent. ليه يعني؟ علشان أنا بقول لك أنت لو هم totally independent أنت حر بقى, ده عامل كده وده عامل كده, وحر في completely independent motion, degrees of freedom. Okay, أنا جاي كده, أنا هاجي أقعد جنبك مش الناحية الثانية, whatever. This is complete independent. That's when I'm constraining this, and انت لو واحد كده لازم الثاني يبقى في البلين دي, يبقى I just constrained one of it. They're not completely independent. There is one constraint, so it reduces dimensionality by 1.
انا ليه كده قلت الديجريز اوف فريدم او الانتجرالز اوف موشن واحد؟ يعني انا قلت ان انا كان معايا 6 بقى معايا 5. ليه كده قال واحد؟
علشان this is a scalar relationship. يعني C dotted with H is one equation. It's a scalar relationship. It's not a vector relationship. Right? Yeah, it's just one equation. So one equation reduces your dimensionality by 1. Okay, if I can find more, then you have the freedom. I mean, انت اللي حصل قال لك ايه ان هو it's perpendicular ده, بس you have the freedom where it is. Okay, you still have the 2 degrees of freedom for that vector. It's constrained to be in that plane. I constrain one of its degrees of freedom, but it's free to point in the other 2 degrees of freedom. تمام؟ Okay? طيب right, so okay, got it. So I'm going to say, okay, so R dotted, R crossed with H, which is the original expression over here, okay? I'm just going to divide the whole thing by mu. Okay, I'm going to divide the whole thing by mu. Okay, so this is divided by mu is equal to C. Okay, I'm going back to here. Is equal to C divided by mu, right? Plus R divided by R. I just move this to the other side. Forget the dot product. Now we're done with this. Okay, so forget that. I'm going back to this expression. I'm moving this to the other side, and I'm dividing the whole thing by mu. Okay, to get that. Right? It turns out, so this is dimensionless, and this is obviously dimensionless. Okay. hold on. This is a vector. It turns out that the magnitude, okay, of c divided by mu, okay, is equal to the magnitude of the eccentricity of motion. And we've derived that last semester, and it's available. It's one of the videos that's available online if you guys want to watch it. But it turns out basically that if I take, okay, so let me one final manipulation. I'm gonna take a dot product. So I'm gonna take a dot with R over here. Dot with this. So I end up with. So this is equal to R dotted with R divided by R plus R dotted with, again, we call this the eccentricity vector, E, okay, is equal to, on the other side, R dotted with R dot crossed with H divided by U. And again, I'm going to use another identity over here, and this is equal to R crossed with R dot, dotted with H, divided by U. This is another identity. Okay. This right here is equal to R crossed with R dot. This is equal to H, dotted with H, divided by U. So this is equal to H squared over mu. Okay. And the right-hand side, again, is equal to R squared over R. Okay. So this is R plus R E cosine theta, which is the angle. For example, with respect to Mars, so now I'm defining, I might be defining an initial position with respect to Earth and a final position with respect to Mars, and this is why we're talking about that we have to do coordinate transformation all over, and you have to make sure that you're not equating something in an Earth-centered with something in a Sun-centered, trying to converge and things like that. So my constraint could be on any components of the velocity, any components of the position. It could be on my orbital elements. Maybe I want to constrain something with my right ascension. I want to constrain something with my inclination. Whatever it is, okay? All these are boundary conditions or constraints, basically, that we place on your system. So in which case, okay, and C2 is straightforward, and C1 you need to take the integral of the system, evaluate it at TF, and find what that is, and plug it into the system, and so on. So we're going to do a lot of these things as we move on, find some analytical expressions for our constants to make it work and fit in my equations. Because if I give you an expression about the true anomaly, constraining the true anomaly, and you want to convert that into another expression to place a constraint on R and V, for example, so you have to derive the analytical expression from what I give you to what you can work with to place in the equation. Yes.
يعني الجراوند فاليو المفروض ان هو يعني يحدد انا همشي ازاي؟
ايه هو؟
restrictions على الباترن اللي انا هاخده ده مقصود بيها الجراوند فاليو اكتر.
It doesn't restrict the path, okay? The boundary value restricts where you're going to be at that location or that time. It depends on what you define the boundary value is. I mean, okay, is it at a specific time? Is it at a specific? Depends on how you design your segments, come in, and so on. So let's say, and then okay, at that time, so I want to get to this location, okay, in that year, at that date, and at that time, because this is the time according to my tabulated ephemeris, the real data. So we're gonna import the NASA ephemeris, okay, and integrate it into your code, okay, that you automatically at any given it a date, it knows exactly where Mars is, where Sun is, where asteroids are, and so on, so you can target, okay? So when I say, all right, so I want to be there, when I get there, okay, I want to have these conditions. Because I don't want to get there at Mars and be too fast that I would miss the capture opportunity. So I want to constrain the velocity that I approach Mars with, for example, okay? Or I want to get captured in a specific orientation for the orbit. So I want to have a specific inclination with respect to the ecliptic, for example. I'm doing a polar orbit, or whatever it is. So you want to constrain that, and so on. Okay? Depending on how many segments you divide your trajectory into, okay? Because we never do like a one-shot thing. Hatta when we did conic sections, we divide them into 3 sections, right? So in every section, you have boundary value problem to solve, okay? Because you want that the final value or the final state in the section to be equal to the initial state of this section, for example. Okay, so it can get captured and so on. So you can define several boundary value problems within the same mission, if you may. Tamam? All right. So in reality, however, f is not constant. Sometimes m command is not constant, but so let's forget about that for a minute, okay? Because we're still considering impulsive maneuvers. We're not into finite burn yet, okay? But in general, it could be a function of time, but f is definitely a function of time. Could be a function of time, could be a function of r, could be a function of b. In our case, it's a function of r. It's not an explicit function of time, but it's a function of position. Okay, defines what the force is. Okay. So yes.
هو انا فاهم ليه مثلا في function of time او function of r بس ليه function of velocity؟
I'm just saying in general it could be. Do you want to think of a system, يعني function of velocity? Dampers.
لا ان او يعني في الاقتصاد بتاعتنا احنا بنستخدم astronauts او orbital mechanics انت هتبقى function of velocity.
In the application that we're working with right now, it's not. Okay. I don't want to say it never is. Just علشان ما بقاش making a false statement. But I'm just saying that I'm just saying generically it could be function of other things. Okay. So what we have here, okay, is I can rewrite this as x double dot, okay, y double dot, and z double dot. Okay, so I break that into 3 different equations. So in that way, I have an f or fx, fy, and this is over m. I'm sorry, over m. In which case you have 3 uncoupled second order differential equations. تمام كده? All right. So we want to use, yes, we can solve this analytically, and the way that just to connect things, and once we had that, okay, to update the location of r at future time, we need to update the true anomaly at the future time, and this is what Kepler's problem is, which we linked, if you guys remember, the older group, the eccentric anomaly and the mean anomaly and the Newton-Raphson methods to iterate and find what the new eccentric anomaly is, and then relating the eccentric anomaly to true anomaly, and then going back here and updating the location of r. Okay. Alternatively, we can do numerical integration. But to do numerical integration, I need to reduce the order of the system from a second order system to a first order system. Okay? So instead of working with the second order system of equation, I'm going to switch that to, I'm going to say, okay, y1 is equal to x, y2 is equal to y, y3 is equal to z, and then y4 is equal to x dot, y5 is equal to y dot, and y6 is equal to z dot. Okay? Right. And then I can take the derivative of that and I say, okay, y1 dot is equal to x dot, which is equal to y4. Okay? And y2 dot is equal to y dot is equal to y5. And y3 dot is equal to y6, okay? And then y4 dot is equal to x double dot, which is equal to the fx over m, okay? Fx over m, and y5 dot is equal to fy over m, and y6 dot is equal to fz over m. So what I've done here, okay, that I changed the system from 3 uncoupled second order to 6 coupled first order. Coupled because in the y dot equation I have y5 appearing, okay, and in the y1 or the y1 dot equation I have y4 appearing, and so on. So they're coupled together, but I reduced the dimensionality or the order from a second order to first order. Okay. Now I can use differential. I'm sorry. I can use numerical integration to solve this. So you guys familiar with the concept of the Taylor series and the Runge-Kutta and how it uses it and all that? Yes. Okay. Good. All right. So what I want you guys now to do. Okay. Let me just bring this up. All right, I want you to code something real quick for me, okay? Using numerical integration, you can use just the ODE 45 in MATLAB. You don't have to write your own, okay? But I just want us to visualize, so we're gonna define the initial conditions for two bodies, okay? M1 and M2. We're gonna define the X and V, or I'm sorry, R and V vectors for both of them, okay? And I want you to plot, you're going to plot it in 3 different ways. You're going to plot it all right. So here are the initial conditions. All right, so I have 2 masses, okay? They're both, so what's unique about this is that they both have the same mass, okay? So the mass M1 is equal to M2, and this is equal to 10 to the 26 kilograms, okay? And then this is initial conditions for both masses. So you have R1 at T0 is equal to 0, okay? And V1 at T0 is equal to 10 in the I direction, plus 20 in the J direction, plus 30 in the K direction, and this is kilometers per second. Okay. And then you have R2 of 0 is equal to 3,000. Okay. And V2 of 0 is equal to 40 J. And again, kilometers per second. Huh? R1 is equal to 0. R2 is equal to 3,000 in the I direction. And then 10, 20, 30, and then 40.
0 degrees in the center of
Okay, so what I want you to do, I want you to integrate this. I want you to integrate this system for 480 seconds. Okay? Integrate the system for 180 seconds and plot. One time I want you to plot the motion of M1 and M2 relative to inertial frame. Okay? And then the second time, plot the motion of M2 and the center of mass relative to M1. اوكي انا ممكن دلوقتي اعمل reference frame اهو تمام. I'm just picking an inertial reference frame. تمام. Initially M1 is right here. تمام. And M2 is right here. Okay, at 3,000 in the I direction. So this is I, J, and K coming out. تمام. M1 initially has velocities in 3 directions. Okay. M2 initially has a velocity in this direction. Okay. All right. So the first step, I want you to integrate, okay, the motion of M1 and M2 with respect to your inertial reference frame and plot that motion. Is that clear? So I want you to the effect of both masses on each other and plot that motion. What is the R1? So you want to integrate R1 double dot and R2 double dot. تمام? Okay. How are you going to convert that into a first order system? What is type? خليني أسألكم حاجة. If you were to define a y vector, okay, what are the components of your y vector for this problem? ما دلوقتي انت you're starting with, if we're going to write this تمام من الاول يعني نقول R1 double dot وهوصل لإيكويشن of that form, okay, اللي هي R1 double dot is equal to negative mu over R12 يعني the mu is the gravitational mass times M1 plus M2. تمام. Okay. I'll get the uncoupled second order differential equation. So I have 2 of those. So I want to convert that into a first order system. تمام. فأنا بسأل دلوقتي إن when I started with 1 كانت الموضوع سهل عندي قلت x y و z و x dot y dot and z dot.